I've always loved CTFs. Not only are they a fantastic learning resource, but also they give me the feeling of competitiveness that I miss from the days when I played football. However, I didn't play CTFs much in the last few years, so I decided to change that. I've reached out to my friends from Just Cut the Fish team, top 12 in the world on CTF time last year. I played with members of this team a few years ago. Now they invited me to play OCTF with them. I knew that tasks on real CTFs are really hard, but I still didn't appreciate them enough, especially that this CTF had maximum weight on CTF time world ranking, which means it should also be adequately difficult compared to other CTFs. During the CTF, I struggled a lot, but honestly, one of the reasons I'm here is to make mistakes and learn from other people, because people in this team are extremely skilled hackers and I can learn so much from them. In this video, I will show you how we solved the "Where are you from" task, which involved two CVEs, AJP request smuggling and the Ghostcat vulnerability. Enjoy! For the task, we had an Apache HTTPD as a front-end server and Apache Tomcat as a backend, and we had no access to the source code. There was no real functionality. The server only responded with some internal IP address, which we didn't know what it meant, and the name of the task, plus having our own instance, suggested a bug like request smuggling, some kind of desync, maybe an SSRF. From server headers, we could judge versions of HTTPD and Tomcat. The frontend server was 2453, which was only one from latest version, which I initially ignored. Tomcat, however, was version 9030, which was from 2020, and I saw that it is vulnerable to potential remote code execution via AJP protocol, and I immediately connected the dot that I saw the vulnerability in HTTPD about request smuggling also in the AJP, which at that point I didn't know what it was. AJP stands for Apache JServ protocol, and it is a binary protocol which is used between these two servers to communicate, instead using an HTTP protocol. For example, instead of wasting 12 bytes in every single request for the content type header, there is a 2-byte sequence that indicates this header, and so on and so on. So when I send GET to the frontend server, it translates this HTTP request into an AJP packet. One request, one packet, nothing interesting. The format of the packet looks like this. First, there are two magic bytes, 1, 2, 3, 4. Next, there is the length of the whole AJP packet. Then, there's a byte that says the type of the packet. In our case, it will always be 02, which means forward request packet. Then, the next one will indicate the HTTP method. The GET is indicated by code 2 and POST is 4. Then there is some data about the request, like the host, the request URI, then there are headers, and finally there are some additional parameters. And that's what happens when we send a GET request without a body. But what happens when we send a POST? It gets a bit more interesting because the body of our request is sent separately from the headers. So we have one HTTP request, but two AJP packets. And that's a good start if you are looking for request smuggling. Our goal is to split these two packets so that Tomcat treats the body of our request as a new request. It's because the AJP protocol in itself gives us a lot of power, and in this particular case, we needed to exploit arbitrary file read on Tomcat. In the packet with headers, there are magic bytes, then there is the length of the packet, and then there is type of the packet and type of the HTTP method. And I would think that the request body would look similarly. I would expect magic bytes as well, I would expect a packet length, and then I would expect some kind of byte indicating that this packet is a request body. But it's not the case. Turns out that in request body, there is no packet type at all, and the packet length is followed by the data length, which in all packets I've noticed was just packet length -2. And then there's your whole body, which is forwarded without any modifications. I didn't read the docs as meticulously when I was solving the challenge, but when preparing for this video, I saw that even the docs say that this seems like a mistake. Because how does the Tomcat know if this AJP packet is a request body with length 514, or is it a GET forward request? Tomcat looks at the previous packet. If it contained the content length header, Tomcat treats the next one as its body. So every time any AJP packet arrives to Tomcat, it asks a question. Did the previous packet contain a content length header? If it didn't, the current packet is a brand new request. If it did, the current packet is a body. So if you could trick HTTPD to send your body of the request in a situation where the previous packet will not have the content length header, you will have the AJP request smuggling. But how do you do this? If you don't send the content length header at all, you get 400 bad requests and you're not even talking with Tomcat. The next idea you might have is to send transfer encoding chunked header. However, when that happens, Apache HTTPD doesn't send the body at all. I didn't find any piece of the documentation that would explain this behavior, but the comment in the source code says that the AJP protocol does not want body data yet. How about an invalid transfer encoding header? When you do this, you also get 400 bad requests. But when you send transfer encoding chunked, chunked, it's valid enough that you don't get 400 bad requests, but it's also not equal to string chunked, which would make HTTPD to get inside the if, which would not send the body. So when you do this, it forwards the request with this header and then sends your body in the next AJP packet. And what does the Tomcat do with the transfer encoding header? I look at the source code of Tomcat and it doesn't even mention transfer encoding header, so I think it doesn't do anything with it. All Tomcat does when it sees our body is asking itself a question. Did the previous request contain a content length header? And in this case, it didn't, so our body is processed as a new request. And this is the first half of the task, which is CVE-2022-26377 AJP request smuggling in Apache HTTPD. And I was reading the analysis of this vulnerability in a Chinese blog post, and of course, back then, nothing was as clear to me as it is now. And there was a payload in this blog post, but I didn't know what it was doing. To understand it, I created a simple Python script to parse the AJP message, which I then extended by the ability to create my own AJP messages. The trick is to make the body of our request exactly 514 bytes long. Why? Because after being hex encoded, it is 0202. And these bytes are prepended by HTTPD to our request. These two packets are forwarded to Tomcat. The first one is processed without any problems. It's a normal AJP packet without the content length header. Then the second packet is processed by Tomcat, the request body. Tomcat asks the question, did the previous packet contain a content length header? And in this case, it didn't, because it contained transfer encoding chunked. So Tomcat does not treat this as a request body. On bytes 5 and 6, there is the length of the packet, but now Tomcat processes it as a new request. It decodes it as forward request method, and in this case get HTTP method. And the rest of our packet must look like a valid AJP packet, which gives us possibility to send requests anywhere and further exploit the second vulnerability. And now it's time to exploit Tomcat. It's a vulnerability where you can use request attributes within an AJP packet that override what you are requesting. So in the original request URI, you said that you want to request index.jsp, which of course is perfectly fine. But then in the attributes, you override this and you say you changed your mind and you wanted to request the web XML instead. This file often contains Tomcat credentials. And of course, you can read any other file that can give you something. However, when solving the challenge, we couldn't get any file read for a long time. The problem was that this was very random. You send a post with your smuggled AJP packet, but the response to it is returned in one of the future responses. And it wasn't the next response or the second next. It could be a few responses, or it could even be a few tens of responses further. And I wasted hours here because I didn't account for that, and I didn't understand why the same things sometimes work and other times they don't. And initially I saw the good error, the error that showed me that the server tried to read the web XML file, but it didn't work, and then for hours I couldn't replicate getting the same error. At this point, I left the task to my teammates and I went on to check another one. In hindsight, it was my mistake, because I was very close to solving this challenge, but had I been doing it alone, I probably would not solve it. Later, our solution to this problem was sending only one post request with a payload, and then sending multiple gets in an infinite loop until we would get a response to the smuggled AJP packet. And the trick that was key to finally solving this challenge had to do with JSP files. They look like this, kinda like templates, and when you request this file, you usually will get the rendered version. However, when your original request URI in the AJP packet is not JSP but whatever else, and then in your attributes you override this to get the index.jsp, then the JSP file is not rendered, but instead you see the whole contents. Inside the index.jsp file, there was just an if that checked the remote address, which had to be equal to a hard-coded one. It was not a problem because it's one of the fields from the AJP packet which we had full control over. This is the final packet that my teammate sent, which gave him the flag. We were one of the 10 teams to solve the challenge, and we ended the CTF at strong 5th place. Thank you for watching this video. If you want to check another write-up from CTF, check out this one, where I solved the challenge created by Live Overflow. For now, thank you for watching and goodbye.